China's Mars orbiter Tianwen-1 has achieved a remarkable milestone in deep space exploration by successfully observing the rare interstellar object known as 3I/Atlas, marking one of the most distant and challenging astronomical observations ever conducted by a planetary probe. This achievement took place in early October, when the interstellar comet made a close pass near Mars, allowing Tianwen-1 to use its high-resolution camera to capture valuable observational data. Despite being approximately 300 million kilometers away from the object, the spacecraft managed to obtain images and measurements that scientists consider among the closest examinations of an interstellar visitor ever performed by a space probe. Interstellar objects are extremely rare and fleeting, originating outside our solar system and passing through it at immense speeds, making their observation both technically demanding and scientifically invaluable. The success of this observation demonstrates not only the robustness of Tianwen-1's onboard instruments, but also the growing maturity of China's deep space mission planning, navigation, and imaging capabilities. According to the China National Space Administration (CNSA), this observation was the result of meticulous preparation that began as early as September, with mission teams carefully calculating trajectories, lighting conditions, camera exposure settings, and spacecraft orientation to maximize the chances of success during the narrow observation window. The fact that Tianwen-1 could detect and image such a distant and faint object while continuing its primary Mars-orbiting duties highlights the spacecraft's versatility and the high level of operational control achieved by mission engineers. The observation of 3I/Atlas is particularly significant because interstellar objects are believed to be remnants of planetary formation processes around other stars, offering a rare opportunity to study material that originated far beyond the influence of our sun. Scientists estimate that 3I/Atlas may have formed around ancient stars near a critical region of the Milky Way and could be between 3 and 11 billion years old, potentially making it older than the solar system itself. This means the object may carry pristine material from an era of the galaxy that predates the formation of Earth, Mars, and other planets, providing clues about the early conditions and chemical processes that shaped planetary systems across the galaxy. By observing such an object, researchers can compare its composition, structure, and behavior with comets and asteroids native to our solar system, helping to answer fundamental questions about how common certain materials are in the universe and whether the building blocks of planets and life are widespread. Beyond its immediate scientific value, the successful observation also represents an important extended mission achievement for Tianwen-1, which was originally launched to study Mars' surface, atmosphere, and geological history. Extended missions allow spacecraft to continue contributing valuable data long after their primary objectives have been met, often by undertaking innovative observations that were not part of the original mission plan. In this case, the observation of 3I/Atlas served as both a scientific investigation and a real-world technical evaluation for future Chinese deep space missions. CNSA has indicated that this effort played a role in testing and validating technologies relevant to the Tianwen-2 mission, which was launched in May and is tasked with sampling an asteroid and exploring a main belt comet. Observing an interstellar object at such extreme distances requires precise spacecraft pointing, stable imaging over long exposure times, and sophisticated data processing techniques, all of which are directly applicable to future missions involving small, fast-moving, and faint targets. The experience gained from Tianwen-1's observation of 3I/Atlas will therefore help refine operational strategies, improve imaging algorithms, and enhance mission planning for upcoming exploration efforts. This achievement also underscores the broader trend of expanding planetary missions beyond their original goals to address new scientific opportunities as they arise. Interstellar objects are unpredictable visitors, and the ability to respond quickly and effectively when one becomes observable is a testament to the flexibility and responsiveness of modern space agencies. Tianwen-1's success demonstrates that China is increasingly capable of participating in this dynamic aspect of space science, contributing valuable data to a field that has so far been limited to only a handful of observed objects. Furthermore, High-resolution imaging of distant interstellar comets can help scientists study how such objects interact with solar radiation as they pass through the inner solar system, including the development of comas and tails, changes in brightness, and potential outgassing behavior. These observations can reveal differences in composition and structure compared to solar system comets, shedding light on the diversity of small bodies in the galaxy. From a technological perspective, the milestone highlights the reliability and longevity of Tianwen-1 systems, which have continued to function effectively well into the mission's extended phase. The spacecraft's ability to perform complex observations while maintaining its Mars orbital operations reflects careful design, robust engineering, and effective ground support. It also demonstrates the value of investing in high-quality imaging systems capable of supporting a wide range of scientific objectives beyond their original scope. As deep space exploration becomes increasingly ambitious, missions that can adapt to new scientific targets will play a crucial role in maximizing the return on investment and advancing our understanding of the universe. In a broader sense, Tianwen-1's observation of 3I/Atlas contributes to humanity's growing effort to study objects that originate beyond our solar neighborhood, offering a glimpse into the processes that shape planetary systems throughout the Milky Way. Each successful observation adds to a small but growing dataset that scientists can use to build models of interstellar object formation, distribution, and evolution. Over time, these studies may help answer profound questions about how common planetary systems, like our own, are, and whether the conditions that led to life on Earth are unique or widespread. The achievement also serves as a symbol of international progress in space science, as discoveries and observations made by one nation often benefit the global scientific community. Data from Tianwen-1's observation may be shared, compared, and combined with observations from ground-based telescopes and other space missions, enriching our collective understanding of this rare visitor. Ultimately, the successful imaging of 3I/Atlas by China's Mars orbiter represents more than a single technical success. It reflects a growing capability to explore the deepest scientific questions using innovative mission extensions, precise engineering, and long-term strategic planning. As humanity continues to look beyond the confines of the solar system, achievements like this demonstrate how even missions orbiting distant planets can play a role in unraveling the mysteries of the wider galaxy, pushing the boundaries of what is possible in deep space exploration and setting the stage for even more ambitious missions in the future. Future observations promise even more excitement. After perihelion, ESA's JWST spacecraft, currently en route to Jupiter, is scheduled to turn its instruments toward 3I/Atlas, adding yet another vantage point. Even more remarkably, calculations suggest that two spacecraft already traveling through space, ESA's Hera mission and NASA's Europa Clipper, may pass through the extended tail of a comet in the coming weeks. If this occurs, their instruments could directly sample ions and dust from an interstellar object, an unprecedented scientific bonus that no one could have planned in advance. Such measurements could provide invaluable data on the composition and structure of material formed around another star. In the end, whether one views 3I/Atlas as a source of sober scientific insight or a canvas for imaginative speculation, its significance is undeniable. It reminds us that the solar system is not an isolated island, but part of a vast, dynamic galaxy where material constantly drifts between stars. While claims of alien technology capture headlines, the true wonder lies in the opportunity to study a genuine interstellar visitor up close, using the full arsenal of modern astronomy. As 3I/Atlas continues its journey, swinging past the sun and fading back into the darkness from which it came, it leaves behind a wealth of data and a renewed sense of cosmic perspective. In that sense, its greatest legacy may not be controversy or hype, but a deeper appreciation of how connected our planetary system is to the broader universe beyond.